Okay, it's my pleasure to introduce our own Sean Andrews from the CFA as today's CFA Colloquium speaker. Sean received his undergraduate degree from Northwestern University, and he went on to do his graduate work at the University of Hawaii. There, he started down the path of observational studies of circumstellar disks and planet formation, using the suite of radio telescopes on Mauna Kea, including the Smithsonian submillimeter array. Sean's initials are, in fact, SMA, but I believe that's just a coincidence. Sean then came to the CFA as a Hubble Fellow, and a few years later he joined the Smithsonian staff as an astrophysicist. He's continued to advance understanding of the formation environment of planets, leading numerous important papers on disk structure and demographics that are based on more and more and better data from radio telescopes, including now the International ALMA telescope in Chile, where he's PI of one of the first large programs. Sean's been recognized with many honors, including not one but two Smithsonian Secretary's Research Prizes, a stint as the Tinsley Visiting Scholar at the University of Texas at Austin, and just last week delivering an invited discourse to the full IAU General Assembly on the topic of observing planet formation, which is the title of his talk today. So let's welcome Sean.
Thank you, David, and thanks everyone for coming out. Hopefully we can, I can explain to you this new ALMA work that we've been doing on planet formation. Before I start, I just want to actually point out the people that do a lot of this, of the work that I'm going to present today. So especially in the latter half of the talk, Jane Huang, who's a graduate student working with me now, Anjali Tripathi, who graduated last spring, and Till Bernsteel, who was a postdoc here with me for 3 years and now is on the faculty in Munich. So I'm going to talk about sort of two subject areas. Most of the time it's going to be spent on this project called DSHARP, and here are my collaborators on that work. I'll talk a little bit about some work that we've done with many telescopes, including the VLA, just to acknowledge some funding sources. Before I sort of get into the details, I just want to set a little bit of context on why you might actually care about planet formation. Does anyone know what this picture is? Yeah, it's the Earth and the Moon viewed from Cassini through the ring system before it crashed into the planet. This is just sort of, I change this slide all the time, but this is sort of, I think, one of the neatest sort of contextual slides because it has rings in it especially. But there's sort of this long-going existential question about origins in astronomy. And it's interesting that in the past sort of 10 years over my career, it sort of becomes less and less philosophical as the exoplanet population grows and grows, that we actually want to understand where we come from and if there are other places like us. That's sort of my philosophical take on things. I hope most people agree. But there's really a much more relevant practical aspect to the planet formation process. And that is if you really want to connect our understanding of the exoplanet population, this is planet mass as a function of semi-major axis of basically all the planets I could find online. If you really want to understand this diagram, you actually have to understand what happens very early on in the formation process of those planets. And the reason is that planets don't stay where they're at in this plane and potentially many other planes. Basically, they form at some radius and then they might migrate as they accrete and grow all over the place. So this changes their atmospheric composition, changes their mass, changes their orbital architectures in somewhat complicated ways, right? All of this is actually happening because of the interaction between these young planets or protoplanets and their birth environment, right? And you probably can guess their birth environment is a disk, right? I like to actually show this just to kind of remind everyone that the idea of planet formation in protoplanetary disks is essentially one of the oldest ideas in astronomy, right? Because you look at the planets in our solar system and they lie along this plane, right? The ecliptic plane. By the way, this is not a planet. I didn't mislabel something that's Regulus. But you have these observations going back thousands of years that people understood, even if they didn't fully express it in that way, that the planetary system, that our planetary system, our solar system, actually formed in a flattened, rotating structure. Right? In the context of our current picture of star and planet formation, this is actually not. This is actually fairly well understood, and disks are actually just the natural outcome of planet formation. So let me just show you this sort of famous and often modified set of slides. But the star formation process starts in a giant molecular cloud, and you might have some dense, overdense core in the center. And the key is that that core might have some rotation as it collapses, right? It undergoes gravitational collapse for some reason. And that rotation basically will turn the structure into a flattened disk-like structure, right? You have some outflows and so on. And eventually, that envelope of material will dissipate, and you're left with a rotating disk. I'm going to focus exclusively on this phase of evolution. We're talking sort of million-year timescales, right? The interesting sort of idea here is that the connection between the formation of planets and the formation of stars is pretty intimate, right? The disks and their hosts actually influence each other quite a bit in terms of the formation of planets and the actual assembly of mass in the star. Right? So I sort of laid this out in the ITC lunch talk, but the big idea in this field is that you measure properties in protoplanetary disks, and you use those to develop and refine a theory that's able to predict the demographic properties of exoplanet systems in our solar system, ideally. But there's sort of 3 points I want to get across that gets into the nitty-gritty of these disk properties. And that is that the real key to planet formation is the evolution of the solids in protoplanetary disks. Right? Now, that evolution happens to be almost entirely driven by interactions with the gas reservoir. And I'm going to emphasize in the second part of the talk, really, that small-scale features, substructures in the gas, are really fundamental to this entire process. Right? So let's start with the first part and do a little bit of a motivation for why we actually care about the solids in planet formation. And this is actually pretty straightforward. Many planets, if not most planets, are actually rocky. Right? This is that diagram I had before, and I just collapsed it into the mass plane. You see this histogram here. It's not that there aren't planets here, it's just that they're actually hard to find. There's a selection effect. This is a model from our Colloquium speaker next week, taking into account those selection effects. But basically what you see is many planets are actually sort of terrestrial analogs, right? Or, at most Uranus, Neptune analogs that have large rocky cores, right? So obviously solids are important in that sense. And we also know that giant planets themselves now have large, massive cores that are solid, right? So Saturn has been known for some time to have a solid core based on, basically measurements of the moments of inertia. And the Juno probe which is what took this picture, has recently confirmed the same thing in Jupiter, right? So obviously the sort of key to assembling these planets is to make the solids form into large planets, right? So one of the issues is that observing the disk solids is in some sense easy, but also difficult. I'll explain in a second. We can observe them up to sort of centimeter size scales in a pretty straightforward way, just by the heat, effectively, that they give off. You tend to emit at a wavelength comparable to your size, so this is sort of millimeter wavelength observations. And we have to do this with an interferometer because the disks themselves in the nearest star-forming regions are pretty small. They subtend less than an arcsecond on the sky, right? So this is the ALMA interferometer, and I'll mostly be talking about ALMA observations. But the key is we can observe solids up to Hubble sizes directly from their thermal continuum emission. Right. So the big issue in planet formation, of course there are many issues, but the big issue that basically has stymied progress for sort of 40, 50 years are growth bottlenecks of solid particles, right? You basically will make a planetesimal. That's the key aspect of the planet formation process. A planetesimal, something like this, which is basically from the Rosetta mission, you basically want to form something that's kilometer scale bodies. if you can form kilometer-scale bodies in a reasonable time frame, there are theories that go back decades that basically say, okay, if I have a population of planetesimals, I can make planets like in our solar system and exoplanets. I'm not going to get into that part of things. But the goal is to get here. The problem is we don't really understand how to get past pebbles, right? So these are actually photographs from laboratory experiments where they take small little dust particles and they drop them in zero-G towers or in the space shuttle. And they actually try and see how particles will grow. And the theory has developed to the point that this is actually well modeled to reproduce the experiments, both experiments and astronomical observations. The path from micron-sized dust particles to millimeter-sized pebbles, sand pebbles in protoplanetary disks is pretty well understood. The problem is when you get to millimeter centimeter sizes, you run into the first major bottlenecks, right? You sort of face your first critical barriers. So that's a long-standing problem in planet formation, but it's also a really interesting opportunity because this is exactly where we have observations. So we have the opportunity to sort of try and understand those bottlenecks and see if we can work our way around them. So I'm going to shift into talking about what those problems are and how they're tied to the gas in the disk, right? And the key issue is the migration of the solids, right? A dust particle does not just sit where it is necessarily. It not only moves, but changes size, right? Obviously, if you want to form planets. So I'm showing here a diagram of just a model of pressure, gas pressure in the disk, right? This is the central star, and here's some puff of gas on some orbit. And this is a force diagram. Your gravity and rotation sort of balance. The issue is, as you can see from the color scale here, is that the gas pressures decrease the further you get from the star, right? This is the standard smooth model that you see in all the sort of textbook planet formation things. The further you get from the star, the densities get lower, just gravitationally, and the temperatures get lower because most of the heating is done by irradiation from the central star, right? So pressure is just density times temperature, and you then have a pressure gradient in the radial direction. The thing is, in that scenario, that pressure gradient contributes some force. It's a small amount, but it's directed outwards, right? And that actually means that the gas, this little gas parcel, is not orbiting at the Keplerian velocity of this orbit. It's orbiting slightly slower, right? And that, by slightly, I mean 1%, right? It seems like a small effect, but it drives all this complicated aerodynamics in the interactions between the gas and the particles. So what happens is for a certain particle size range, those particles start to decouple from dynamically decouple from the gas. And what happens is that they actually want to move at Keplerian speeds, but they're embedded in a medium that actually is moving slower than Keplerian speeds. So that makes them feel a drag force. It's like sticking your hand out of a car window. You feel that drag force. They lose angular momentum and they spiral in towards the pressure maximum, which in the standard planet formation model is near the central star. So that migration is called radial drift in this model, similar analogous things in many parts of astrophysics. And I tried to find a good slide for it, and if you look it up on Google, it's bad. Radius bone and bad injuries. Or you see Vin Diesel movie posters. But the key problem here is that when you get these particles moving quickly, you get larger relative velocities, and then when the particles encounter each other, they don't hit and stick. They can be destructive, and then you're moving backwards. You're fragmenting grains instead of growing them. That's an issue, but the bigger issue is that the time scale for this drift motion is so much shorter than the time scale for collisions, right? That basically by the time you can find a partner to grow to a larger size, you've moved, right? So drift effectively halts growth. And it just so happens, I'll show you in a slide in a second, it just so happens in the outer disk that this happens to pebble-sized particles, right? So this is the same model. This is models I did with Till Bernsteel a few years ago. This is the same model, and this shows the radial velocity as a function of radius of particles of different sizes. So micron-sized particles in green, centimeter-sized particles in pink, and negative velocities are in towards the central star. These are non-standard, non-IU units of AU per 1,000 years. It's my favorite velocity unit. But it illustrates the point. If you're sort of at tens of AU, you're also moving inwards on, at few AU per 1,000 years, right? So very fast. If these disks are 1 million years old, you would deplete the solids in this mass reservoir very quickly, right? Just so you know, the gas is moving pretty much like the micron-sized particles. So the consequence of this is actually pretty straightforward, and that's actually that you get a size segregation, radial size segregation for different particles, right? So this is the surface density profile as a function of radius, and the pebbles are actually concentrated in the inner disk. Micron-sized particles are concentrated further out, right? So this is the sort of standard theoretical prediction, and the problem is it happens too fast to be consistent, A, with observations, and to have any hope of forming planetesimals, right? So this is probably, if you've heard of this before, this is probably familiar to you as something called the meter size barrier, right? Because this maximum radial velocity at 1 AU happens to be for meter size particles. So we try and actually measure this observationally to get an idea if it's really happening with the efficiency that we think. And this was the subject of Anjali's, some of Anjali's PhD work. What we're measuring here is just a color, right, in the radio wavelengths, a spectral index, as a function of radius from spatially resolved observations at multiple frequencies. That's the gray swath here, right? And the yellow is a model, right? It gives you basically the same kind of behavior. The particle size segregation gives you a radial color variation. You have larger particles at small radii. Larger particles are grayer or redder. They give you a lower spectral index. And then you have only small particles at large radii. So you get spectral indices like what you see in the ISM. So from micron-sized particles. Right? The sort of insight that Anjali had was that you can look at this in a different way, and instead of modeling, this is what that gray swath is modeling data, you can actually just measure the sizes, right? So these are like half-light radii. It's a function of wavelengths, and you can see that they actually decrease. So larger particles, centimeter-sized particles, have that emission has a smaller radius than the disk. So that's great. If you look at these, again, this is a model. This is not fitting the model to the data, right? This is just a model in a suite of calculations. And it just shows that you can basically get this to work for this particular disk. We see this in every disk that we have resolved multi-frequency observations for. You can reproduce, you can get this kind of behavior in basically every disk. The real problem is I've sort of fudged something here to make a point. And that is that this model is for the wrong age, right? It's actually for much earlier time frames than is consistent with the observations of the host star, right? So that is pointing to this efficiency problem. There's a time scale issue, right? You basically can't get this to work for the right times. And the point is that by the time you get to 1 million years old, the models predict that you should have basically depleted the outer reservoir of the disk of pebbles, and basically you've lost the chance to grow planetesimals, right? So this is a long-standing problem, but it's also had a pretty long-standing solution, which I'll get to in just a second. But the key is that you don't have a smooth gas profile, right? That's the insight. And that insight came here in 1972 from Fred Whipple, right? In a paper that actually is just remarkably prescient. It's a conference proceeding, so it's remarkably prescient and has like 3 plots in it that sort of contain all the important aspects of the field in one thing. It's interesting because it basically is presented as such that it doesn't present a reason for it, which I sort of like because it'll flow in the context of this talk. But let's just say we have a pressure profile here where this is a big ring. The pressure is depleted, densities are depleted in here. And then we compare the force diagram again. I've taken out gravity and rotation from these things. This is the gray here is at the maximum pressure, right? So the maximum pressure, a parcel of gas is then now moving at the Keplerian velocity. So particles there don't feel any headwind. If they get there, that's where they're going to stay. If they're a little bit inside, the pressure gradient is positive, and they'll actually be accelerated and sort of flung out into the pressure maximum. And on the outside, it's the same as I described before. You migrate into the pressure maximum, right? So instead of migrating to a global maximum in the inner disk, you migrate to a local maximum. This is pretty straightforward perturbation to the general problem. In the pressure maximum, you actually have reduced relative velocities. Collisions are less likely to be problematic, and growth is a little bit easier. But the key point is that basically the time scales for drift are very, very long compared to the time scales for growth. Effectively, if you had no diffusion, if you had no turbulent diffusion, you would have an infinite drift time scale. Of course, that's not exactly true. So here again is our fiducial planet formation, or the fiducial physical scenario for planet formation models, right, where you have a lot of very rapid radial drift. And if I perturb the pressure profile, you get a dramatically different behavior, right? Radial velocities, you see this pressure trapping effectively there. The key point actually is if you perturb the gas density profile with a large amplitude pressure or density variation, you get a very strong concentration of pebbles at the local pressure maximum, and smaller particles as well. The key point here is that you start to get solids to gas mass ratios of order unity. And when you get solids to gas mass ratios above 10% or something like that, there are a number of fluid instabilities, including direct gravitational collapse, where you can form planetesimals from small particles very rapidly, orbital period type rapidly. Right? So this is the key. This is how you would actually form planetesimals in these strong concentrations of pebbles, right? In this little ring at some location. Right? So we've been observing these things for 7-8 years. I think the last time I was in front of you giving a colloquium here, I was talking about these types of objects called transition disks. And basically what you see there are rings, right? You see sort of this star is at the center of these images, which you can't actually see because it doesn't emit in the millimeter continuum, but you have these rings of emission, and that's a concentration of millimeter, centimeter sized particles induced by some local pressure maximum, right? So, should we have known, or should we have concluded from 7 or 8 years ago that this was the solution to the planet formation problem? Sort of, but not really. The problem is that the population of transition disks is small, right? You see maybe 10% of the total population looks like this, and the rest of them don't, right? So it's not actually a solution to have these nice, perfect annular structures that concentrate particles. And it's especially true because we know that now from ALMA, these are SMA images I should mention, we know now for ALMA for these same disks that things are a lot more complicated. It's not just one ring, and it's not just symmetric, and so on, right? So that sort of pushes to what I would say is the sort of, again, epsilon-type perturbation on the model. This is not like, this fiendish, devious solution. Instead of having a large pressure perturbation, why don't we just have a small one, or a lot of small ones, right? So if you have a suite of sort of subtle pressure variations, right? So if you look here at the gas density profile, this is the perturbation. It's sort of 10% amplitude perturbations. This is a toy from Paolo Pania. This is just a sine wave imposed on that same gas pressure profile I've been showing you. It actually doesn't take much. The small perturbations in the gas really amplify the concentrations of the pebbles, right? So you get this complicated velocity profile, but the key point is, again, you're still getting sort of 10% solids to dust ratios in these concentrations, right? And so you could potentially form planetesimals there. So like I said, this is just, it's really sort of like a genius paper because it's so simple and analytic, and it gives you the opportunity for the solution, but it's not physical, on purpose. The question is, are there physical origins for behavior like this that we can understand, right? So there are a lot of them, as you might imagine. People are writing papers about this all the time. But I sort of like to break them down into two categories. One I would say is sort of fluid dynamics, I guess a better way to put it is the dynamical interactions between gas, dust, and things like magnetic fields or turbulence, where you can have things like a global gravitational instability or MHD turbulence, creating structures and so on. The point is that in this scenario, this sort of picture, the perturbations actually concentrate the solids, and then you make planetesimals. This is sort of the egg and the chicken and the egg problem. So the substructures actually help you make planetary systems. But there's a sort of different interpretation, and that is basically that the perturbations are actually a sign of young planetary systems, right? So if you dynamically interact a planet, as I said before, a planetary mass companion with the disk, it will repel material out of its orbit, and you'll create these substructures. You can even get pretty complicated instabilities. In that case, if you can actually measure perturbations like this, you can learn something about the masses and architectures of planetary systems at their formation epoch, and directly tie it into the planet formation thing. This is sort of, for me, this has been sort of uncomfortable, right? This gets all the attention, of course, right? All the theorists want to write planet-disk interaction papers. But the idea is basically that you need substructures to form planetesimals, and you're creating planetesimals in effect by using planets, right? So there's sort of a logical circle. So at first I found that kind of disconcerting, but then the point is basically actually more, important. And that is basically, if this is the thing that's actually happening, it means that the whole picture for planet formation is sort of wrong. It means that this stuff operates on very short time scales, and you probably create planetesimals effectively instantaneously during the star formation process, and you can make planets really easily. So if you can confirm this is what's going on, it really does change the whole picture for planet formation. So, if anyone's noticed, I've talked for like 25 minutes and I've barely shown you an image. So let's start showing ALMA images. Actually, these are actually not ALMA images. These are SMA images and KARMA images. And until a few years ago, these were the highest spatial resolution observations of disks. This one partly because it's nearby. It's sort of a cheat. But you get sort of 20 AU resolution, and you don't see a whole lot. These are normal disks. These don't have these large rings or cavities or so on. But when you increase the resolution or improve the resolution by a factor of 10, you see that they're just riddled with substructures, right? So the question is, this is HL tau. This is sort of done as part of a commissioning campaign with ALMA. And this is TW Hydro, which we did a couple years after that. So you're seeing structures on AU scales, right? This is an actual 1 AU resolution image. Again, this is the nearest disk to us, so it's sort of a cheat. And this is kind of interesting because we're finally at the stage where we can actually use the very longest baselines of the sort of premier interferometer in the world, 15, 16 kilometer baselines, to access these spatial scales where we expect all these small perturbations to be happening. Right? And at the same time, people were actually finding evidence for these kinds of substructures all over the place. Right? These are actually scattered light, infrared scattered light observations of disks, where you're actually seeing starlight reflected off very small grains in the upper atmospheres of the disks. And even there, you're starting to see structures, which suggests that the structures are actually genuinely in the gas phase, and we're picking them up as tracers in the continuum. And here's a suite of lower resolution ALMA continuum images, again, sort of 1015 arcsecond or 1015 AU resolution. We're actually starting to see these the larger population of substructures appear. Right? So you can see the direction where this is going. It's trying to actually get a better handle on what the substructures are doing in the planet formation process. So we've been running this program for about a year now called DSHARP. Well, it hasn't been called that whole time. The idea is to basically get some idea about the population of substructures in these disks. Right? So this is what's called a large program in ALMA, where you ask for a lot more time than you normally would. It's still, 70 hours is still a lot of time, but it may not seem that large to people familiar with optical telescopes. 10 nights of observing or something like that. But when the oversubscription rate's 7 or 8 to 1, it's very difficult to do more than a few tens of hours. So we tried to do this last summer and ended up getting stuck doing it last fall, which wasn't ideal for these targets. But we have basically 20 observations of 20 disks. And the goals are actually pretty basic at the top level. It's just to understand how frequently you see these substructures, what kind of forms they take, and then their properties, their spatial scales, their symmetry, their amplitudes, and so on. We're targeting a 5 AU resolution. That corresponds roughly, over most of the disk volume, it corresponds to the sort of average gas pressure scale height, which is basically where you'd expect the planetary type perturbations or fluid instability type perturbations to be manifested. And it's pretty deep, observing at 1 millimeter observations. So the nice thing about this kind of project with ALMA is that you sort of sign on to provide the data. ALMA has an archive, of course, and it provides raw data and some calibration scripts. But you have to do a lot of extra work to do that, and so we're providing images and profiles and all this stuff to the community as the papers come out in this fall. Right, so these are the images of those 20 disks in the 1.3 millimeter continuum. And you can see that basically just a quick observation shows you that they're just rife with substructures. In fact, every disk has something in it that's sort of at the scales of the resolution, sort of few AU scales. I'm going to try and kind of guide you through some of the basic features and things we're taking away from these observations, right? So I'm taking a few sources away. I'll get back to them. But basically, the thing you see most frequently are these sort of concentric rings and gaps. We're calling them depletions of emission and enhancements of emission, right? That's a pretty simple structure, but the properties are pretty diverse, right? So in all cases, they seem concentric. In most cases, they're symmetric. I'll get back to that in a second. But they're located everywhere. Everywhere there's continuum emission, all the way into 5 AU, basically our resolution limit, and all the way out to 150 AU. You see them everywhere. They have different widths. They have a wide range of amplitudes. The interesting thing is now I've ordered these by host luminosity, the stellar host luminosity. We have a wide range, basically cover the full stellar mass spectrum. And there's no connection between the hosts and the locations or amplitudes of the substructures. And that's sort of important in the sense that it tells you basically that something that's related to the temperature or gravity of the system is not what's ultimately responsible for the structures. The key sort of idea that people have had has been that you slow down the migration of particles when you cross a volatile condensation front. You basically change the material properties of the particles and it no longer migrates as if it's that size. That doesn't seem to work, at least for this sample, because you don't have this relationship between the temperature structure of the disk and not. Right? So I said, this is a paper that Jane's preparing right now, one of the two papers Jane's preparing right now. I said symmetric, but that's not entirely true. There's two cases where the symmetry is broken in some specific regions. You see these little sort of arclets. These are two other papers that we're working on. These are pretty rare, so 2 out of 20 in our sample, actually. They're not as rare in the transition disks, and that might be pointing to the issue, right? So a lot of dynamicists are surprised by how symmetric everything actually happens. And it tells you that, I'll get to this in a second, but it tells you that if it's a dynamical perturbation, the typical masses of the perturbers are low. Right? So this is where I'm just going to get into some speculation on the origins of those gap and ring substructures. And I should say I wouldn't say this is settled on our team, but this is my personal opinion since I have the bully pulpit. I think it's pretty clear that these rings are actually tracing pressure bumps. Part of that comes from the scales, right? They can be considerably narrower than the local pressure scale height, and that's just not a stable situation if they're not actual trapped particles. And if you do some modeling, as Case Delamond is doing, here's some examples. If you do some modeling of simulations that are basically trapping particles, you see that you typically need you typically can't have much diffusion, right? The turbulence must be relatively low. And that makes the densities, the particle densities in these pretty high, right? So they're pretty much right at the level where they're consistent with instabilities to kick in to form planetesimals. And if we look at sort of the suite of these ring gap systems, I find it very hard personally to believe that it's not actually tied to planet-disk interactions. I think that's really the solution. This is an observation of one disk, right? And this is a simulation that was not tuned to this. This is part of a large suite of hydro plus particle simulations that Xiangjie Zhang and Xiaowan Zhu are doing. And you might think, oh, well, this is a model with 8 planets or something, like however many gaps you see. But it's one planet, right, located in this dark gap, sort of Saturn mass planet. And so the key point is that basically there's not a one-to-one correspondence to a substructure and a planet in these models, right? So it's a little easier to swallow when you see these multi-gap systems. Again, you need viscosity low, so turbulence must be low. And the symmetry tells you that the perturbers would be low mass. So some of the simulations are suggesting sort of super Earths up to Saturn mass, and maybe an occasional, in one of the asymmetric cases, a Jupiter, right? So there are other options, right? There are sort of more complicated options. It's a little harder for me to assess those because they're basically tied to non-ideal MHD effects. This is something that Xuening Bai worked on when he was here, and he's part of our team. The problem with those is that they're not yet capable of using numerical simulations to make predictions for what you'd actually see. So it's a little hard to assess those. But if you adopt this idea for their origins, and we go back to this planet mass versus orbital semi-major axis, it's interesting because to create the population of substructures we see, this is the kind of perturbers that you would actually conclude are there, right? So a few things about this. One, obviously it's tracing a part of the population that we don't currently have access to. Ideally, eventually you'll have access to these kinds of things, maybe not all the way down here, but you'll have access to these kinds of things from direct imaging. But of course, to do that, you need a 20+ meter telescope and a very good AO system. And even still, it's a little hard to get to the bottom half of these things, right? So you'd have to hope for the next generation space telescopes. Another thing about the planets, though, that's sort of interesting is, right now, these are all safely beyond detection, right? So, I can just stand up here and tell you that it's planets and no one can prove me wrong, which is great. But it's an opportunity to actually look at a different part of parameter space to do that. And eventually you want to make a connection up here to actually find a perturber. Okay. So let me go back. I showed you this original slide. Let me go back and talk about the things that I didn't show you, these remaining 5 things, right? So these 2 sources are actually spirals. They're a little hard to see in the projection, but you can see in the polar projection where this is azimuthal angle as a function of radius. You can see it a little better here. You get these sort of fingers, right? If these were rings, they'd just be vertical, right? Now these 2 sources are special because we know they have companions. They have stellar companions, right? You can see one of them right here. The other one's a little off chart. I'll show it to you now, right? So there's one perturber. There's one, this is sort of 0.1 solar mass star, another one over here. And then there's this system. This in here is a very close sub-AU binary. Has its own gap and ring structures in it. Don't ask me what that means. So what we do see in the cases where we have a known perturber and a known fairly high mass ratio, you don't necessarily get gaps and rings, at least around the primary. You get 2-armed sort of tight spiral structures. Right? We go back to these guys, and I'll get rid of those 2 that I just showed you. And you can see the last 3, these are isolated stars. They are not in multiple systems, at least not with a mass ratio that we can detect anything. And they have these enormous, complicated spiral structures. They're largely sort of 2-armed spirals. And if you look at the polar projections, now you can see these arms more clearly. Right? Jane is working on this as well. these are pretty complicated, and the reason that they're pretty complicated is in the middle of these spiral patterns, there are concentric gaps and rings. So you see that one here, there's a gap, here's a gap. And over here, there's a gap as well, but it's a little harder to see. Even stranger than that is these arms seem to cross the gaps. Right? I like this a lot because I have absolutely no clue why that's happening. And it's probably the one thing that we'll publish in this initial tranche of papers that no one could be like, my model shows this already. This is not a predicted thing, and I don't know what's going on. It could very easily just be multiple things happening at the same time. So let me give you again, my personal thoughts on the spirals that we actually see. And this, in the case of the ones that are in multiple systems, this is actually basically what hydro simulations predict. You have dynamical perturbations and tidal truncation basically stripping off material from the outer disk, and you get this spiral mode as well. It is not dissimilar from what you see in interacting galaxies here in M51. This is just the standard sort of gravitational interaction, right? So there's a lot of interesting comparison to hydro models that could be done here. But in the isolated systems, it's a little harder to understand what's actually happening. And my sort of personal opinion is that what we're probably seeing is evidence for a global gravitational instability, standard sort of tomb ray instability. And the reason that I think that, well, one, theoretical models actually look a lot like the sort of m=2 type spirals that we see. But the other thing is the three disks that actually show this structure happen to be the largest and coldest disks in the sample, right? And that actually is just much more conducive to the tomb ray instability as well. But I don't know what to make of those additional substructures at this point. So let me give you a few key takeaway points from this project. And that is that, as far as we've looked, and as far as I know, there are other examples of this sort of isolated objects floating around waiting to be published. As far as we can tell, is if you look at a disk at sort of few AU angular resolution, everything is loaded with substructures, right? This is just a ubiquitous feature. There's not an obvious pattern. There's just a wide variety in the scales, not so much in the forms, although there's different kinds of forms. They're mostly symmetric. The scales and amplitudes are different in all sources. And I suspect actually that, well, I'm quite confident that we're seeing evidence for the particle traps, and I suspect that we're actually seeing perturbations that are tied to young planets. Now, the interesting thing about this is basically that, if this part is true, and even if it's not, this picture of a sort of corrugated or perturbed gas pressure profile in a protoplanetary disk, it doesn't necessarily negate all of the theoretical work on planet formation, but it does tell you that it's fundamentally important to understand the disk at sort of AU scales, because that is going to drive the evolution of planetary systems. It's responsible for forming them, but then it will actually drive the evolution of those systems. And the reason is basically, say you even form a planet and there's a gap induced by some MHD effect, right? That planet's migration will actually be affected by the substructures in the disk, right? It can even stop and turn around, right? So it's really just sort of that these smallest features are the fundamental aspect of protoplanetary disk evolution and planet formation. Okay. So I'm just going to finish up by just reinforcing a few points. One is that planet formation, it really is, our understanding of it hinges on a good understanding of the evolution of disk solids. And the solids actually evolve because of their fairly complicated interactions with the gas reservoir. That's crucial. It's problematic, but it's also crucial because that's how you shepherd particles together to allow them to grow into planetesimals. The substructures of these disks that we're now observing actually facilitate planet formation, and they may also actually trace the early generation of planet formation. And basically, you couldn't do this until a couple of years ago, right? You basically need millimeter observations on sort of 30 milliarc second angular resolutions, right? And that basically only happened in the past few years with ALMA. So I'll just leave it at that, take questions.
Sean, on these disk that you've measured in the continuum, are there comparable maps made with in the gas, like molecular maps, and do they trace similar structures, or are they different?
That's a good question. I don't have a slide, but we did observe 12 CO at the same time. The problem is, right, so these are sort of 1-hour integrations, and to really map the lines at this same resolution, you need like an order of magnitude more time. But there are a few cases, a few of the sort of best cases, where indeed you see substructures in the 12 CO line as well, rings usually in the 12 CO line. And sometimes they correspond to dust features, sometimes they're nearby, right? Because the problem with the 12 CO is it's actually forming in a much higher layer of the gas, right? So and then to deplete it is really hard, right? Because even a tiny poof of CO becomes optically thick. So these are really strong gas density perturbations, I would say, or pressure perturbations. The interesting thing, I think, is that in the 12 CO lines, these continuum maps have a limited extent. They go to 100 AU at most or something like that. But in the gas lines, you can actually see gaps going out much further, well beyond where you see the continuum. So the substructures continue, right? So that'll be interesting. That's obviously a natural follow-up. And Jane has 1 or 2 programs to do deep, like 10-hour integrations on specific sources. That's basically what you need. It's not the kind of project you can cram in for that. Karin has another large program, which probably upsets people, but the two protoplanetary disk large programs came to our group so far. But anyways, to do chemistry at comparable resolutions, so slightly backed off of the resolution a little bit, but to look at many different lines. I mean, the nice thing to do would be to look at an optically thin line, because the intensity in an optically thin line is pressure, effectively. I mean, modulo abundance, but it's pressure. So then you'd want to do a 1-to-1 identification of pressure maximum. It's actually quite a bit more complicated than that, but yeah, that's what's going on now.
So, a significant fraction of mature stars are in binaries or higher order systems, but binarity doesn't seem to play a very dominant role in this story. Is that a selection effect?
Yes, that is. It wasn't intentional, right? But in order to basically convince them to give me this much time, you sort of have to build on previous work at coarser resolution, right? So this is the stuff that I've been doing since I came here with the SMA, quarter arc second resolution, and we did a surface brightness selection to make sure we'd have the sensitivity to see small perturbations at high resolution. And what happens is basically when you do a surface brightness selection and you look at the sources that we actually have already looked at, you pretty much exclude most binaries automatically. So it's sort of an implicit selection effect. There are binary surveys going on, but not at this resolution yet. I do think, given the spiral structure you see there and the opportunity for interfacing with the hydro stuff, there's a great project there, right? Just exclusively seeking out the binaries and looking at their structures, but it hasn't been done.
So what are the time scales? If you go back a decade later, would things change on at least the iterations?
Well, the orbital timescales, they're just orbital time. These are roughly solar mass stars, right? So no, they're changing in the inner few AU, but below our resolution level, right? So there's, the idea is basically, if you look, the very inner parts of these just become optically thick, even at a millimeter wavelength. So you need to go to longer wavelengths, centimeter wavelengths, to have any hope of actually seeing perturbations. But say you had, you would need infinite time on the current VLA, but you wouldn't need infinite time on the potential NG VLA that is being designed. And that will have much higher resolution as it spreads from basically Mexico to Colorado. I don't remember where it's going. And then if you saw an asymmetry in a ring at 1 AU, right, you could just go back 6 months later and watch it move, right? But, it would presumably be moving at a Keplerian speed, but it sort of depends on what kind of instability is generating it, and if it's a perturber or not. But yeah, that's definitely a long-standing idea for things like SKA, which now you can't do, but and NGVLA if it's built.
So Sean, what's the evolutionary stage of those objects?
They're all class 2.
A few million years? Or
Yeah, a million years. They're all sort of class 2
do you see
disks.
any difference or trends?
Well, there's only one or two. There's very few cases where you actually have, I would say, a believable age gradient. Right? So TW Hydro, which I showed you, was also perfectly symmetric rings, and people would say HL Tau, which is younger, although of indeterminate age, also has perfectly symmetric rings. There's a couple of cases in an earlier evolutionary stage where there's still envelope that you also see rings and gaps and stuff as well. But it's pretty, yeah. I don't trust any real age gradients across the sample.
So this may be pushing a little too far, but some of the lower brightness outer rings you have in these images, there appears, at least in the images, to be a lot of non-antimutual structure. Is that noise or is that real?
So this thing is real. This sort of cruff around here, this is the lowest signal to noise source. That's not, as far as we can tell, that's consistent with noise. Yes, you can ignore that. Yes. And there's also cases where it's actually not easy to image these things, right? You're sort of, so you get these little sort of knots around the rings. Those are reproduced if you make symmetric models and then image them like they were in the data. So that's in some cases you have imaging tricks to get rid of those things. But yeah, that's a good question.
Any more questions? All right, well, if not, let's thank Sean again.